Lesson 7.4, parallel lines and proportional parts. Okay, as a review from 7.3, it's like it's been a while. We can determine if triangles are similar if we can show that they have at least two congruent angles. That's angle, sim. If we can show that their three sides all have the same like scale factor or are proportional. Or if we can show two sides are proportional and the included angle is congruent. Okay? Those are our three basically like ways of showing and determining if the triangles are similar. And number one, I didn't have any side lengths given to me. So the only possible way I could show that these are similar is by angle. A couple ways you could do this. We have vertical angles. You could say those are congruent. And we also have parallel lines here. So you could think of these other sides of the triangle as like transversals, and we have alternate interior angles. Those would be congruent. Similarly, these ones. So this one you should have said yes. Angle, sim. Okay. Looking at number 2, I have one pair of congruent angles, the right angles. But I don't know anything else about the other angles. These are definitely not vertical angles. There's no parallel lines. And I see I have some side lengths. So I'm thinking probably side angle side because I don't know the third side, but I know the included angle. All right, so however you want to write the ratio of the corresponding sides, I usually start with like my bigger triangles, like 20 to 15, which you can reduce that ratio, divide them both by 5. That's like 4 to 3. So you got to check if that ratio is proportional or is the same as the ratio of the other corresponding side, which would be the 24 to 18. Does that reduce to 4/3? 4 to 3? Oh, they're both divisible by 6. Yeah. So the sides are proportional. Included angles congruent. So yes. Side angle, side sim. Before we do any calculations on number 3, what type of similarity do you think we're going to look for? Side, side, side. We're given 3 sides, right? We're given 3 sides. Okay, so I like to start with my bigger triangle when I set up my ratios, and I like to start with my largest side. So 40 would correspond to the largest side in this triangle, to 10, which reduces to 4 to 1. So you can even think of that as like your scale factor, your ratio. All right, next largest side, 32 to 8. Also reduces to 4/1. Okay, so far we're good. The first 2 sides are proportional. And then this one, the smallest, 28 to 7. Nice. Also proportional. So this one was another yes. Side, 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 sim. So there's one of each example. Angle, side, side, side. This one's looking like a side angle side setup. I have this included angle of the 2 given side lengths, and they're telling you it's congruent. So let's look. We'll start with this one. 14 to the longer side. This would be 10. Reduces to 7/5. Since I start with this triangle, I gotta do that again. So 8 to 6. That's 4 to 3. And no. Not similar. The side lengths are not proportional. Okay. Questions? That was 7.3. How's the quiz yesterday? How's the ACT? Are you on
Right.
Don't do that.
Why?
I don't have to give you the Heimlich.
I'm not going to.
Spit it out, please. I'm serious. Throw it away. I don't want you to choke right in front of me. I'm concerned about your safety.
They have holes in them you can breathe.
What? That's scary. True story. This is really sad. Not to bring down the mood, but one of my friends, her daughter was like 4 and was like biting to try to get a cap of a glue bottle off, and she choked and died from it. So scary. Okay, seriously.
Talk about dead children vampires. Let's
I
go.
know, right? That's alright. You just saw that in your mouth. Same with like when people chew on caps, like that really scares me. Do you want to go recycle that so you're not tempted?
No.
Okay. All right, folks.
Should have said no.
I want the cap.
We have a couple new theorems today, and some of them involve triangles, but they're really more like proportional work. Okay, similar to what this chapter is all about: proportion and similarity. All right, first one here: triangle proportionality theorem. So if we have a line that's parallel to one side of our triangle and it intersects the other two sides, look at my setup here. BE is intersecting AD and AC, and it's parallel to this third side. Then it's going to divide each of these two sides into proportional lengths, okay, as long as these are parallel. So if these are parallel, then the ratio of this length, we'll say AB, of this like chunk of this segment that BE like splits it into, the ratio of that chunk to this chunk is going to be proportional to that same ratio on the other side of the triangle that it intersects. So this one, AE to ED. Now, like all proportions, you have to be consistent with how you set it up. You could also say, like the smaller chunk, BC, to the larger, but then you'd have to do the same for the other side. And then it'd be ED to AE. So as long as those two lengths are parallel, that relationship's going to be true. It's going to split the other two sides into proportional lengths. Okay? Here's an example. I did have like a nice, like kind of like visual. I'll see if I can find it after this. In this triangle, they're telling us that RT is parallel to VU, which is shown using these arrows. RT is parallel to VU. Then they give us some of these measures that are marked on my triangle, such as this segment right here is 3, VR is 8, UT is 12, and they want us to find SU, which they're labeling X in this diagram here. All right, so according to this theorem, as long as these are parallel, this little segment here is going to split each side into proportional lengths. Okay, so let's set up a ratio with my red one. So I'm gonna go from the parallel base. So from R to V, 8 to 3. That's gonna be proportional to the same thing on the second side. From the base, 12. The green marker sucks. 12 to X. All right, so again, you gotta pick how you want to write the first ratio, but then you have to be consistent in the proportion. Just like all proportions, we can cross multiply to solve this. You can either reduce that to 9/2. You could say 4.5 if you want as well. So that's the length of SU. I'd probably do a decimal if I'm talking about the length of a piece of a triangle. So again, you could have done your ratios 3 to 8, but then the second one would have had to been X to 12. That's basically the triangle proportionality theorem. Let's try a little bit harder one with some algebra. Okay, they tell us to identify the similar triangles here. So we do actually have some similar triangles because of these parallel side lengths. So I'll do this one in red, my smaller one. And this one. Now we do know some side lengths. For example, in my blue triangle, I know JL is 24 units long. But because these are parallel, I can find some congruent angles, and I can easily kind of like prove these are similar by angle similarity. First of all, actually, a really easy one. What angle do both the triangles share that's going to be congruent to itself? Nope. What angle do both the triangles have? L. Reflexive property. That's going to be congruent to itself, right? Okay. All right, now I have parallel lines here. If it helps you to kind of extend them, you can. Who can tell me why this angle would be congruent to this angle? Here's my parallel lines. Here's my transversal. What kind of angles are those? Nope. I think you said it. Corresponding. That was the C one you're looking for. Corresponding. Good. Corresponding. And then same thing here. Like we could say these ones are also congruent. But basically, we can say that these triangles are similar. So I'll do my triangle, the small one. KML is similar to JNL by angle, sim. Now they didn't really ask me to like prove it. It just said identify which triangles are similar. So that's kind of a review. Then find each measure, now knowing about this new triangle proportionality theorem, which tells us that as long as this segment is parallel to one side, that's this side, it's going to split, and don't say bisect, because bisect means split in half. It's going to split each side into proportional lengths. So this distance to this distance is going to be proportional to the same on the other side, this distance to this distance. Okay, small problem here. I don't know this distance KL. Ideas? Lillian?
You subtract 24 by 8.
Right, we know the whole side is 24. We know this little piece is 8, so this has to be 16. Okay, so now I can set up this ratio. That's 16 to 8. So I'm being cautious about how I'm setting up this proportion. If I do this 16, this like longer side or from L, I have to be consistent with the other side. So I have to go from L, 6x plus 2. It's going to be proportional to those two segments as well. All right, now if you're tempted to start cross multiplying, you can. I'm just going to give you a little piece of advice on these. You're going to make your equation life easier if you simplify your ratios. Okay, so for example, 16 over 8, you could reduce that to 2 over 1. And you don't really need to write 2 over 1, but it does help you kind of if you still want to cross multiply. But it just makes you work with a little bit smaller numbers when you go to cross multiply and solve the equation. So I always like to do that after I kind of like set my proportion. I look like, hey, is there anything I can simplify before I do my cross multiplying here? So then I get 6x plus 2 times 1, which is 6x plus 2, 2 times x plus 5. Distribute and solve. All right, now if I'm looking back at the directions, it doesn't say find x. It says find each measure. So what they want me to find is the measure of NM, which now that we know x is 2, NM is going to be 7. Now, without doing any math, obviously I know you could plug 2 in here really quick and crunch that number, and that's fine. We also know that the ratio of these two sides is the same as this one, so that longer segment, since it's 2 to 1, has to be double that length, right? So it's going to be 14. But again, if you're like, I think I'd rather just plug this in and do 6 times 2 is 12 plus 2 is 14, that's fine. But also recognize your relationships and those ratios. Sometimes it will save you some time. Ooh, the next thing's exciting. I almost forgot. Do you guys remember, flashback to like chapter 2? Do you remember what a converse of a theorem is?
Opposite.
What do you mean by opposite?
Reverse.
Okay, keep going. You're right. Either of you.
So like, if something, I don't know, an example.
And the converse is side, or no, the converse is the angles, and then the other one's like the side lengths, or something like that.
I don't know what you're thinking of, but maybe. I'm just thinking of straight up like if-then statements, like what a converse is.
Oh, if the if is true. Oh wait, no, that's not it.
No, Tyson, you think you know?
You take the final product to get to the start of the theorem.
I think you're thinking inverse.
Oh.
Maybe. Okay. One last guess.
No.
It's good. You just flip flop the hypothesis and conclusion.
Wow, that was a lot more complicated.
Remember that? So if it's like if A then B, the converse is if B then A. You just flip flop the hypothesis and conclusion. Okay. So, maybe if that's what you're trying to say. Right thinking. So basically, the converse of that theorem we just talked about is also true. So if you know that these lengths of some segment that splits it are proportional, stop it, then we can conclude those lines are parallel. Okay, so it's just like flip-flopping the hypothesis and conclusion. So if we can show, let's say, this ratio of AE to EB. So if it separates it into two proportional parts, so then CD to DB, if those are proportional, then we can conclude that segment that intersects those two sides is parallel to the other or the third side of the triangle. In this case, it would be AC. Okay, so let's try an example of like using the converse. So here in this example, it says in triangle WXZ, XY is 15, YZ is 25, WA is 18, and AZ is 32. So it's basically giving you the length of all these little chunks. All right, let's fill these in as we go here. So XY is 15, YZ is 25, WA is 18, AZ is 32. So as long as we can show that AY is splitting those two sides into proportional pieces, then we can conclude WX and AY would be parallel. All right, so let's set up a proportion here. Well, first let's set up a ratio. So I would do 25, I always like to start with the longer one, 25 to 15, which divide those both by 5, 5 to 3. Let's see if that is the same as the ratio on my other two. Ooh, what's the GCF for 32 and 18? 6 doesn't go to 32. It is actually only 2. Uh-oh. Are those proportional? No. So, it says determine whether those lines are parallel. No. WX, here's how you can write it in math language. WX is not parallel to AY because ZY to YX is not proportional to ZA to AW, meaning 5/3 does not equal 16/9. Okay, we're going to try one more with this little theorem. That's a little bit more challenging. This one says, find how long AD has to be so that you can determine DE and AB are indeed parallel. Okay, so you're like, well, how can I do that? I don't know a ratio of anything. Let's just try and set up a proportion here. So on this side, obviously the two sides that DE are intersecting are this red side, CB, and this green side, CA. So I'll just start down here and go up this way. So 8x to 3x, or like the larger chunk to the smaller chunk, is that proportional to, well, we're going to make it, we're going to find x so that this is true. So that 5x to 2x minus 4, so that is proportional. Okay, now before you start cross multiplying, as I told you, I like to simplify before I cross multiply. Anybody know what happens here with an x over x? Yes.
You can divide by x.
Okay, what do you mean by that?
You can divide by both x, and you just take numbers.
Okay, you're actually like right. I don't want to say dividing both sides by x because technically then you'd have to do it on this side too. Well, what is x? What is anything over itself reduced to? 1. So x over x is really just a big ol' 1, or you can kind of think they like cancel each other out. But really you just have 8/3 times 1. 8/3 times 1. So that does just leave the numbers. Good job, Alejandro. And now this becomes a lot easier to cross multiply. Okie-doke. 8 times 2x minus 4 equals 3 times 5x. 16x minus 32 equals 15x. I'm a fast cross multiplier. I'm going to move the 15 over here and get 60 minus 15 is 1, and I'm going to move the 32 over as well. And, okay, we have to find AB, not just x. No problem. AD is 2 times x minus 4. So 2 times 32 is 64 minus 4. AD is 60 units. As long as AD is 60 units, those would be proportional, meaning DE and AB would be parallel. All right, next theorem. The triangle mid-segment theorem. We talked about trapezoid mid-segments. Do you remember this? So as long as the mid-segment, you don't have to write this down, intersected the midpoint of the legs. Do you guys remember what the length of this was? It was always like half the distance of
The average.
the average. Yep. So you add those up and divide it by 2. So this is kind of similar, except you don't have a trapezoid. We have a triangle. So because it comes to a point, you can almost think of that as like no distance. And this just ends up being half the distance of that third side that it doesn't touch. Okay, so that's one of the things we're going to talk about. So again, a mid-segment is a segment that connects the midpoint of 2 sides. So this one right here is my mid-segment. You can have more than one mid-segment in a triangle. Obviously, I could make a mid-segment that connects the midpoint of FG and HG if I want to. Okay, so as long as this is a mid-segment, so in this case, as long as J and K are midpoints, and obviously that segment then, JK is connecting the 2 midpoints, then we can conclude 2 things. Then we know that mid-segment is going to be parallel to the third side. Because obviously it's splitting into proportional parts, right? They're congruent. And what I was just talking about, JK is going to be exactly half the distance of that other side of FG. The mid-segment is going to be half the distance of that third side. Okay, don't let this picture confuse you. It's giving you 2 different mid-segments. So it says of triangle ABC, DE is a mid-segment and so is EF. All right, I'm going to start by just drawing in DE here. DE is a mid-segment, which means it connects the midpoint of this side and the midpoint of this side. So according to this theorem, as long as it's connecting the midpoints, which it is because it's a mid-segment, then that means it's going to be parallel to this third side, and this lane is going to be exactly half of the side that it's parallel to. Okay, again, same as a trapezoid, but just think you're averaging it with nothing on that opposite side. So if they ask me to find the length of AB, well, I know that that mid-segment length, DE, is going to be half of what AB is, and you probably don't really need to set up an equation to figure this out. We know DE is 5 units long, so what's AB going to be? No, careful. This is half of this. 10. 10 units. Now, if you're thinking of it in like an equation, careful here. You can either times both sides by 2 to get rid of this. 5 divided by 1/2 is not 2.5. 5 divided by 2 is 2.5. 5 divided by 1/2 is the same as 5 times the reciprocal is 10. Careful. Fraction. All right. Next one says find FE. So now they're talking about this other mid-segment. Oh no. Pictures always move on me here. Okay. Now they're talking about this other mid-segment FE, which, since it's a mid-segment, it's going to connect these midpoints and this other side. So this time, the mid-segment's parallel to that third side, BC. Okay, see that? Now these are my parallel lengths. They want me to find FE. This time I know that opposite side. I know BC is 18 units long, so I know that the mid-segment is exactly half of that distance, half of BC. So it's going to be half of 18. FE is going to be 9 units. Okay, this is a fun little add-on question that doesn't really have anything to do with the triangle mid-segment. It's just more what we know about parallel lines. This is find the measure of angle AFE. Okay. Let me put back those parallel. We know these lines are parallel because ED's a mid-segment. So sometimes it helps too to extend the parallel lines. So you can think of FE as a transversal. And if they want us to find this angle measure, and you're like, oh, I see this one's 87. What relationship do we have going on here? Alternate interior angle. See that? Alternate interior angle. So that one's also going to be 87 degrees. I would put this in your notes so you know why. Almost done. Okay. The next one is just kind of applying this more than just triangles. So if we have a bunch of parallel lines, even 3, or it could be more parallel lines, and maybe we have some other transversal, this property that they cut them proportionally is always going to hold true as long as the lines are parallel to each other. Okay? So in this example here, you can see that they're marking all of these are parallel. So as long as the lines are parallel, then any transversal it intersects, such as this one, ABC. Well, I shouldn't call that line ABC. Line AC, if you want to call it. It's going to split it up proportionally. So the ratio of AB to BC is going to be proportional to EF to FG. And we could add another one if we wanted to, and it's always going to split it into proportional segments. Okay, this next part was kind of interesting. It says use the figure below to find x and find y. So they're marking all these parallel lines. So I see I have a couple transversals. Looking at this one, I notice that this parallel line right here not only split it into proportional parts, but into congruent parts. So an easy way to find x is because they marked that those are congruent, would be set them equal to each other because they have to be the same length. All right, we can solve this. X is 6. Awesome. A couple ways you could go about finding y. You might be tempted to like plug 6 back in here and find like these actual lengths and then set up a proportion, which would be fine. But if we know they're proportional, if it splits these into two congruent pieces, what's it going to do to this one? It's proportional. Let me write it out this way. If I plug these back in, I get 11 and 11. So if I write that as a ratio, that's just the same as a ratio of 1 to 1, right? To itself. So these are also going to be congruent. Now you could also, if you didn't recognize that and you got caught up in like setting up the proportion, you could do this. You could say, all right, so 11 to 11 has to be proportional to when it's splitting up the green one. And you could do it. It's just going to take you a little bit longer. Obviously, reduce this to 1 over 1. But like I was saying, guys, if it's going to split it up proportionally, that would mean that these would also have to be the same, which you would get by doing the cross multiplying. Okay? If the relationship from this to this is that they're the same, and this is proportional, they also have to be the same to themselves. Is what I'm trying to say. All right, solve this quick. So y is 2. That's just not always going to be the case, that they're equal to each other. I just want to look at that one example together because I think it's kind of interesting. All right, we're just going to do a couple word problems here, and then we'll call it a day. First one. In this figure, Davis, Broad, and Main Streets are all parallel. Let's mark it. They're all parallel. The figure shows the distance in between the city blocks. Find x. So I see in between Davis and Broad along South View is 24, and then Broad to Main is 8. And then along Bridgeview, Davis to Broad is 15, Broad to Main is x. Okay, so let's set up a proportion. So I'm going to start with the one I know, the 24 to 8. Since these are all parallel, is going to be proportional to 15x. Same as before, I like to reduce the ratio. That reduces to 3 over 1. You don't have to. You'll get the same answer. Just makes your equation solving a little bit easier. Either way, we should get x to be 5. And that's all we had to find was x. Not bad. All right. Let's try one that's a little more fun. Ms. Henchurch is building a 2-story jungle gym according to the plans shown. Find x. Oh boy. All right. So they're showing me these right angles. Because hopefully if I'm building a jungle gym, it's not off at an angle, right? That'd be dangerous. So, how do I want to think of it? If I'm thinking these are a bunch of rectangles, these are the parallel lines they're trying to show you. My 3-story jungle gym. I can do this. Actually, I think I've been using blue for my parallel lines. Let me be consistent. Parallel, parallel, parallel. So one transversely here, one kind of segment, these are splitting, is this 8 to 10. I'm going to start with the larger one if I write that ratio, 10 to 8. And then looking over here where I'm trying to find x, I have another transversal. So if I went 10 to 8, I'd have to go x 2. Uh-oh. What's this, Lane? Nice, Lauren. 24 minus x. I'm impressed. 24 minus x, right? If that whole thing's 24, this would be 24 minus x. Okay, before you cross multiply, reduce the ratio if you want. Cross multiply. Ooh, this is good stuff. Okay. Remember how I said I don't love mixed numbers? Well, I don't. That's still true. But when we're talking about measuring, we kind of do use mixed numbers a lot, right? If you look at like a ruler or something, you might say like 4 3/8 of an inch or something like that instead of an improper fraction. So here we probably should, in your calculator you're going to get this, which is technically fine. These units would be feet. But how we'd probably typically see that written is like 13, what's 0.3 repeating as a fraction? 13 1/3 foot, or, that's good. Or, how many inches is a third of a foot? You could say 13 feet, 4 inches. If you want to. There's a little math in real life for you. Okay. That's it. I pass up worksheet?